Welcome to the Math Help Room, your YouTube resource for all things math. The title of this lecture is The Domain of a Function, and this is lecture 2 in our Pre-Calculus series. So in this lecture, we're going to examine how one can determine the domain of a function that is defined through an equation, and we will look at 3 different examples of functions that illustrate these general principles. We start then by defining the domain of a function. The natural domain or implied domain, or simply domain for simplicity, of a function f that's specified by an equation y equals f of x is the subset of the real numbers consisting of all those real numbers x for which the expression f of x can be meaningfully evaluated. We will say that an expression can be meaningfully evaluated if it does not involve operations that are undefined in mathematics, examples of which are dividing by 0, taking an even root, such as, for example, the square root of a negative number, or, for instance, taking the logarithm of a non-positive number. There's many other conditions like these in general, but we will focus on these 3 in this lecture. If no such operations occur in the expression for f of x, then the domain of the function f is simply the entire set of the real numbers. We start by looking at an example, that of the function f of x, which is 2x plus 1 divided by x squared minus 5x plus 6, and we want to find the domain of this function. So in this function, the only potentially troublesome operation is dividing by 0. So we need to exclude those real numbers x from the domain of this function for which the denominator x squared minus 5x plus 6 becomes 0. So prompted by this, we solve first the equation that asks when is x squared minus 5x plus 6 equal to 0. This can be easily solved once we recognize that the left-hand side can be factored as x minus 2 times x minus 3, and then setting that equal to 0 leads to 2 solutions, x1 equal to 2 and x2 equal to 3. So we conclude that the domain of our given function f is the set of all real numbers with the exception of 2 and 3, as those 2 numbers lead to zeros in the denominator of the function. So we can write our domain for this function as either r minus 2 comma 3, meaning we take the set of real numbers and exclude 2 and 3 from it, or using interval notation, we can write the domain of f as a union of 3 intervals, those going from minus infinity to 2, then from 2 to 3, and from 3 to infinity, with endpoints being excluded in all 3 intervals. Lastly, this fancy r that we use, again as a reminder, stands for the set of real numbers. In our second example, we consider the function f of x equal to 1 over the square root of x plus 3. The domain of this function includes all those real numbers x which are subject to 2 conditions. Namely, we want x plus 3 to be greater or equal than 0, and this is so that we may be able to evaluate the square root of x plus 3. And also we want the square root of x plus 3 to not be equal to 0, so that we may divide by the square root of x plus 3, which occurs in the denominator of this function. So both conditions are rather easy to evaluate. The first condition simply leads to x greater or equal to negative 3. In the second condition, we want to find those x for which the square root of x plus 3 is non-zero, and we do that by first solving the equation the square root of x plus 3 is equal to 0. Looking at this equation, we square both sides of it to arrive at the equation x plus 3 is equal to 0, which leads to the unique solution x is equal to negative 3. It follows then that the square root of x plus 3 is non-zero for all real numbers with the exception of x equal to negative 3. Combining the 2 conditions in the red rectangles leads to the final solution for the domain of this function, namely as being the interval from minus 3 to infinity. Our first condition said that x need to be greater or equal than minus 3, but the second condition says that x cannot be equal to negative 3, as that one yields a 0 in the denominator. In our third example, we consider the function f of x equals 1 divided by the natural logarithm of x minus 1. So recall that in general, a logarithm function log with base a of x is only defined for those x that are strictly bigger than 0. The natural logarithm ln of x is simply the logarithm function log with base a of x, where the base a equals to the natural base, generally denoted by e, which is equal to 2.71828 and so on. So e, the natural base, is a transcendental number and has an infinite number of decimals. For a point x to be in the domain of this function, we require two conditions. Firstly, we require that x minus 1 be bigger than 0, and this is so that we may evaluate the natural logarithm of x minus 1. But secondly, we also want the natural logarithm of x minus 1 to be non-zero so that we don't end up dividing by 0 in the denominator of this function. Again, both conditions can be easily evaluated. The first of these conditions simply says x needs to be strictly bigger than 1. To evaluate the second condition, meaning to find those x for which ln of x minus 1 is non-zero, we first solve the equation that asks when is the natural logarithm of x minus 1 equal to 0. To solve this equation, we exponentiate both sides with base e. That is, we transform the equation which says the natural logarithm of x minus 1 is equal to 0 to the equation that says e to the power, the natural log of x minus 1, equals e to the power 0. From here, we observe that on the left-hand side, e and the natural logarithm, being inverse functions of one another, cancel out and leave us with simply x minus 1, while the right-hand side, e to the 0, is evaluated to 1, leading to the very simple equation x minus 1 is equal to 1, the solution of which is x is equal to 2. It follows that the natural logarithm of x minus 1 is non-zero whenever x itself is not equal to 2. Combining again the two conditions in the red squares, we are led to the final solution for the domain of this function as being the union of two intervals from 1 to 2 and 2 to infinity, with all endpoints excluded, or we can write this as a single interval from 1 to infinity with the point 2 excluded from that interval.